All right, so we've talked about crystallographic points, directions, and planes, and now I want to talk about density, and particularly density along one of those directions, so linear density. All right, so linear density represents the packing, like we talked about with atomic packing factor in the previous section, but this is along a particular direction. And so we are talking about basically the fraction of occupied length. So if I pick a length like is shown here, this is a 110 direction. I want to know the fraction of occupied length along a given direction. So how much of it is occupied by atoms or ions and molecules. And so in this case, a linear density of 1 would mean that the atoms are in contact and there's no empty space along that direction. So you kind of see that in this direction. The atoms are touching there and there, and so this is all occupied space or direction. And so this has the highest possible linear density of 1. So I want to bring up an important point here. So the definition that we're going to use, the linear density definition here, is that the highest density is 1. We define it differently than the book does. I don't really like the way they do it. They do a number density, so you get basically certain amount in nanometers per length. I think this is better because it's a fractional amount and it's easier to compare values. So again, we are going to use the definition here in the slides, and it's going to be different than the one in the book. So if you're looking at the book for this section, make sure you note the differences, and we are going to use the ones in the slide. It will be the same for planar density in the next section as well. So let's get to that definition and the procedure that goes along with it. And again, it's a fairly straightforward definition for linear density, or LD. But basically what we're going to do is we're going to look at the number of radii within the unit cell and multiply that by the radius. So how many radii do we have? Multiply it by the radius. And then that's going to be over the length of the direction within the unit cell. So again, it's a fraction of occupied length. And so we're constraining that to within the unit cell so that we have a comparable length of the direction, which is infinite, right? So we just define it within the unit cell. So number of radii within unit cell times the radius over the length of the direction within the unit cell. All right, so typically you're going to be given a direction, right? So you'll want, if that's not already sketched, you want to sketch the direction. So like you saw the 110 in the previous diagram, you'll want to sketch that. And then the next step after that is you'll determine the direction length in terms of the lattice parameter. So basically determine the length. And we know if it's a cube, we know the edge length is A. If we have a different type of unit cell, then we may have A, B, and C. But in this case, just in terms of A. And then you want to count up the number of radii, R, along that direction within the unit cell. And then, like we did with atomic packing factor and some density calculations, we want to find our relationship between A and R to be able to convert, right? Because right now we have A and we have R. They aren't going to cancel out until we have that relationship. So at that point, we can reduce and solve for the linear density. So let's look at the linear density for the 0, 1, 0 direction that we see here in this simple cube. So it's a simple cubic system. So here I'm showing you that space filling model with the unit cell. And so we'll go through the procedure here. All right, so I draw the direction, and I'm drawing it up here in the front so that you can see it, because keep in mind, the origin is relative, so we can put that wherever we want. And so I'm drawing the direction here. And sometimes it's more useful, since this is a three-dimensional model, it's useful to redraw it and just plane. So I redraw it over here just so that you can see it if it's a little confusing from the three-dimensional model. So basically I have two large atoms This is the corner that you see here, and then the corner over here is here. So that's what I see, right? So I sketched the direction. I showed that this is length A, this is R, the radius, and so that's the first step. All right, so now I determine the direction length in terms of A. So here, this one's easy, right? Because it's one of these 1, 0, 0 types, which is our edges of the cube. So that's going to mean that the length within the unit cell is the same as the lattice parameter. So A is the length of the direction within the unit cell, right? Because we're talking about this length, and that is the same as A. All right, so we've determined the direction, or the length of the direction, which is A, 1A. And so that's the same as, if it's a cube, that's the same as any side. And so 1, 0, 0, 0, 1, 0, 0, 0, 1, any of those have the same, which is the lattice parameter. All right, so now we need to determine the number of radii along that direction. So from here to here, count up the radii. So we see that going from here to here, this is 1 radii. And then from here to here, this is 1 radii. So we have 2. All right, so 2 radii along that length. All right, so nothing too tricky so far. All right, so now we find our relationship between A and R for the simple cubic arrangement. And this is one where we actually use the same length, right? So because when we tried to find a relationship between A and R, we wanted some length like A here, in which there's no empty space, right? You see that the atoms are touching in this space-filling model. And so if I look at A, it has 2 radii and there's no gap, right? So if I looked at, for example, this dimension here, you see a lot of gap. So you want to find a length where there's no empty space. So this length. And so that means that A is equal to 2R with nothing else. So we have that. So 2 radii along that length. And so that is our relationship for simple cubic. We know A is equal to 2R. So now we're going to plug all this in. So we have 2 times R as the length of the, or the number of atoms. And so basically that's the length of atoms within that direction. And then A is equal to 2R as well. So this should be a sort of self-fulfilling property because these are close packed, they're touching, they're close packed. That means that there's no space, and that means that the density should be 1 because it's completely filled. So this is kind of a check confirming this is the close packed direction. So that's nothing too crazy with this one, but we'll work an example in the next module.